In this video, I'm going to introduce one model of chemical bonding called the Lewis model. So the idea behind this unit is that chemical bonding is really at the heart of chemistry. So when two molecules interact or if two atoms come close enough together to form a chemical bond, then that's when chemistry can actually start to happen. And there are three bonding theories, and the first one is the Lewis model. We will also talk about the valence bond theory and the molecular orbital theory a little later, but for now we're just going to focus on this first one here. As for which one is correct, we can't really say. It's not like there's a right one and a wrong one. Each of these models explains a certain phenomena that we see. And so remember that theories have explanatory power, so they are able to help us explain how things happen. And so as we start with the Lewis model, what this does is it will help us explain how atoms combine to form molecules. And then when we get to the valence bond theory and molecular orbital theory, that will help explain the shapes of these molecules and how they can move about in a 3D environment. So why do we even care about the molecular shape of something? Well, it helps us understand properties of molecules and how they behave in chemical reactions. So if we don't know how a molecule exists in 3D space, we can't predict how it will interact with its neighbors or other species in space. So this is something that lets us actually make predictions and solve scientific problems. And they also play key roles in our senses. So when you taste something, what's happening is a compound is binding to a receptor in your tongue and sending a signal to your brain. And so without these interactions, we wouldn't be able to experience our world in the same way. So in one interesting example, there is a compound that when it's the same, all the same atoms that are connected in the same way, but the shape is slightly different, and one tastes like spearmint and the other tastes like, I believe it's cardamom. So there's a real difference there in taste, and it's just because of the arrangement of the atoms in three-dimensional space. So we also use this for drug discovery. So our enzymes, which pretty much drive chemical reactions in the body, they all have receptors that have specific shapes. And they can really only recognize and act on molecules of a specific shape. So as an example, last April, scientists figured out how an antibody bound to that SARS-CoV-2 virus. Okay, so this was that information that came out and that helped guide the drug and vaccine design. And this is actually how we ended up making the vaccine. So what they found was that the coronavirus has a spike protein, and it is that spike protein that binds to something on our cells, and that's what allows it to enter the cell. And so scientists were able to look at that spike protein and change it, and that's basically what our vaccine is. It's a mutated spike protein. It doesn't make us sick, but it still allows our body to make antibodies and fight off the virus. Another example is the drug HIV protease. So a protease is an enzyme that chops up a compound. And there is this drug, and what it does is it inhibits the HIV protease. And so what they found was, here is this, it's called the active site. So it's like where the chemistry happens on the protein. And scientists were able to design a molecule that fit perfectly in that active site that would disable this enzyme that HIV needed in order to replicate and survive inside the body. And so while this drug does not cure HIV, and it will not affect AIDS if the patient's already progressed, but what this drug will do is it will inhibit HIV from replicating in the body, and so it will keep the viral load very low, and so that will prevent the person from developing AIDS. It will prevent the person from getting sick and likely prevent them from transmitting the virus to others. So this was a huge breakthrough in HIV/AIDS research. Okay, so now that we've talked about why bonds are so important, let's take a look at how they actually form and why they form. So really, what we're talking about is lowering the potential energy of atoms. So in chemistry, basically what's happening is we want, or we don't want, but the molecules move towards lower energy. Minimizing energy is the name of the game. So minimize energy, maximize entropy. We will talk about that more in the third quarter. But what I want you to know right now is that the whole idea is to lower the potential energy. And so when we say atoms, we really mean electrons. So the atom has that nucleus that doesn't do anything unless we're dealing with nuclear chemistry, which we're not going to talk about this quarter. So we're really talking about what goes on with the electrons. So this is a map. You can kind of think of this as a a graphical representation of Coulomb's law. So what you see is two species will repel each other. And then as the potential energy drops, there's some overlap and attraction. And then as they get closer and closer together, and then as they get further and further apart, there's no overlap and no attraction. So the idea is if they're too close together, they're repelling. And if they are below some threshold, when they hit that sweet spot of overlapping orbitals, that's where that chemical bond is forming. So for example, two bromine atoms, they repel each other if they're too close together, but when they get to be the right distance, that is where they form that covalent bond. That's where Br2 would form. So I want to take a minute and talk about the three different types of bonds. Now, I know that your book uses the terminology ionic bond and metallic bond, although I personally do not like these terms because they're not really bonds. A true bond is a covalent bond where there's an actual sharing of electrons. With an ionic bond, what it really is a very strong electrostatic attraction between a positively charged ion and a negatively charged ion. In this example, it's table salt, positively charged sodium and negatively charged chloride. Over here, they call this a metallic bond. Again, this is really electrostatic interactions or charge interactions, where the purple dots are sodium ions and the electrons kind of surround the ions in a sea. Okay, so why do these things look like this? Well, metals have a really, really low ionization energy because they lose electrons really easily. Non-metals have a large electron affinity, and so they gain electrons. And so when you work with a metal and a non-metal, what happens is the electron leaves the metal because it has a very low ionization energy. It's easy to lose an electron. And then the non-metal, since it has a large electron affinity, it's really easy for a non-metal to gain an electron, so that's what it does. And now there's a +1 and a -1, and they interact with each other because opposite charges are attracted. So another idea is the covalent bond. So it's two non-metals. Non-metals have a high ionization energy, so it's really difficult to remove electrons from these compounds. So these compounds don't readily lose electrons, and so they share the electrons. So a hydrogen and an oxygen, instead of one of those taking the electron away from something else, they share it, okay? So they can both see the electron, they both have access to it, but they're sharing it. For a metal, what you end up having is this organization of the cation, and then these electron clouds just surrounding them. And so all of the atoms in the metal lattice are sharing all of the valence electrons. So you can kind of think of it as like a smear of electrons over this. So imagine if you had one of those toys where you have those magnetic balls that like you can stack, and they all stick together, and then you smeared like peanut butter over it. So the peanut butter would be like the electron cloud, and the nuclei would be those little metal balls. So now that we've looked at different types of bonds, we are going to look at the Lewis model. So here's his guy, he's playing with this chemistry set here. And what this model focuses on is the behavior of valence electrons. Okay, so remember from our last chapter, they are the electrons that are important for bonding because they are the outermost loosely held electrons. So we are not talking about the core electrons here. These do not participate in chemical bonds. We are only speaking about the valence electrons. So our main group number tells us how many valence electrons an atom has. So with our group 1, they always have 1 valence electron, and group 2, they always have 2. And then remember, these are our transition elements, so we're not really going to focus on these guys. But then we jump over to this other side, and so this would be 3 through 8. You might also see it written as 3A through 8A or 13 through 18. These numbers here show you how many valence electrons are in the group. So every atom in this group has 7 valence electrons. Every atom in this group has 6, 5, 4, and so on. So after Lewis, we name these things Lewis structures. You may have also heard of them called Lewis dot structures. And so what we do is we represent these valence electrons with dots. So if we look, here's our core, so we don't do anything with these guys. We're going to look at just our valence electrons here. And we've got 2s2, 2p4. So we have 2 s electrons, 4 p electrons. That's a total of 6 valence electrons. So we take our oxygen and we put the dots around it, and we have 6 dots around our oxygen. Now, just like when we filled orbitals, we want to put them around in single and then double them up. So it would be 1, 2, 3, 4, 5, 6. So now we see that there are 2 unpaired valence electrons and 2 pairs of valence electrons. So this kind of shows you how to do this. So with our sodium, magnesium, aluminum. So if you want to practice, just pick any row in the periodic table and you know how many valence electrons you have. Practice drawing this around. So here's our example. Remember, we don't want to do it this way because electrons don't pair up until they have to. So you can draw it either way. These are equivalent. So it doesn't matter to me where the dots go as long as you keep them separated until you've run out of separate spots. So the first 4 have to go around our symbol. The first 4 dots have to go around the symbol individually, and then you can start doubling them up. But as for which ones you write down first, that part doesn't matter, as long as they are separate if you have enough space to do so. So what you might notice is that our last argon has 8 electrons in its valence shell. And so this is where we get our famous octet rule. So in the Lewis model, chemical bonding is governed by the octet rule. And what that means is the s and the p orbitals are full of electrons, and they are the most stable. Now you might be thinking, well, what about the d orbitals? Okay, yeah, so the octet rule doesn't work for every single atom, but that's okay, because remember, these models, they have strengths and weaknesses. One of the weaknesses of the Lewis model is it doesn't work very well for the transition elements, but it does work really well for a lot of compounds, especially in the first two rows of the periodic table. So that's where we get this octet rule. So if there's 8 electrons in this valence shell, then the potential energy of the compound is minimized, and there's really no more room to accept more electrons. So in other words, the noble gas configuration, they're full, they cannot accept any more electrons, and so they are the most stable. So you might have heard or seen the phrase, this atom wants to be a noble gas. That is not true. Atoms don't, first of all, they don't have desires, and second of all, it's not turning into a noble gas. What that actually means is that the atom is more stable when the electron configuration matches that of the noble gas in the row above it. So, for example, sodium is more stable when it matches the noble gas configuration of neon, and potassium is more stable when it matches the electron configuration of argon.